Very good evening to one and all. And on behalf of the organizing committee of the sixth lecture workshop on transdisciplinary areas of research and teaching by Shanti Swarup Bhatnagar Awardees, I would like to now welcome our esteemed expert for today, Professor Anish Ghosh from School of Mathematics, Tata Institute of Fundamental Research, Bombay. And I would like to apprise all the attendees that this particular webinar is part of this month-long series, which is actually the sixth workshop, which the Indi-Delhi Upadhyaya College is jointly organizing with the National Academy of Sciences, India, Allahabad. And this is under the aegis of the DBT Star College Program, that is the Department of Biotechnology's Star College Program, which is funding 5 departments, that is botany, zoology, chemistry, electronics, and mathematics. And because of pandemic, we are holding this workshop in an online mode. And that's one of the benefits I can say that we are drawing it from here. Otherwise, getting such an busy persons and all the experts from all across India, it would not have been possible for us. So before I ask Anish to deliver his talk, I'll briefly introduce him to all the attendees. He's a professor at the School of Mathematics of TIFR, Mumbai, and specializes in ergodic theory, Lie groups, and homogeneous spaces and number theory. He received a BSc degree from St. Xavier's College, Mumbai in 2001, and received his PhD degree from the Brandeis University in US in 2006 under the supervision of D.Y. Klinbaugh. After spending a short period as a postdoctoral fellow at the University of Texas, Austin, he joined the faculty at the University of East Anglia, UK. During this time, his research was supported by the US NSF and the UK EPSRC and the Royal Society. In 2014, he moved to TIFR as a faculty member and has been the recipient of several recognitions, including the Nasi Scopus Young Scientist Award in the year 2017, DST Swarn Jayanti Fellowship in 2017, and the BM Birla Science Prize in the year 2017. He was elected a Fellow of the Indian Academy of Sciences in 2018 and was awarded the Shanti Swarup Bhatnagar Prize for Science and Technology in Mathematical Science in the year 2021. Yes, with these words, I now invite Anish to kindly share his screen. Let us talk.
Okay, so thank you very much. So I'd like to thank Professor Saxena for organizing this wonderful event and for inviting me to give this talk. It's a great pleasure and a privilege for me to speak to you. Of course, I would have been much happier to do it in person, but since circumstances are difficult, we must manage with an online mode of communication. So I work in an area of mathematics called Ergodic Theory and Dynamical Systems, and especially like to explore connections of this theory with number theory. So my aim today is to somehow just give an introduction to the kind of mathematics that I do. So it's an open-ended talk. If we come to the kind of work that I do, fine. If we don't, that's also fine. For me, the most important thing is I'd like to communicate some ideas to you. And in order to do that, it's also important that you should stop me if you have any questions. Don't hesitate. Any question is always a useful question. And it also gives me some energy to hear questions from the audience during the lecture. All right. So let me begin with trying to explain, some of you might have, there's something in the chat. Maybe I should have a look at it. Is it a question? Oh, I see. Yes, yes. Please also type questions in the chat. Okay, so some of you might have heard this term ergodic theory before, or maybe it's not familiar to you. In any case, let me provide a 2-minute historical introduction. So ergodic theory is a branch of mathematics which had its origins in physics, in statistical physics. Excuse me. So for example, suppose you were to inclined to study the motion of a complicated particle like a gas molecule. Okay. Now, all of us, we are quite good at doing problems in Newtonian mechanics, like train leaves from one station to another train leaves from the third station, when do they meet, and so on and so forth. So these are very good physics problems, but they have some kind of idealized setup. Okay, so many assumptions are made. As we all know, as we are all science students and scientists, that real life is very different. So for example, applying Newtonian mechanics to some complicated gas or a molecule is very difficult. So the physicist, the great Austrian physicist Boltzmann, initiated the study of ergodic theory by formulating what is called the ergodic hypothesis. And this hypothesis says that if I have some extremely complicated chaotic particle moving around in a closed space, then I may not be able to predict precisely the motion of this particle. However, under certain conditions, I can say what happens over long periods of time. So more precisely, it says that over a long period of time, if you enclose a chaotic particle which satisfies these ergodic conditions, then the particle will somehow fill up the space evenly, to equidistribute, okay, in this case. All right, so this is kind of a motto for today, which is that systems which are very complicated and seem to be very chaotic, nevertheless exhibit a lot of uniformity in a certain sense. And this uniformity in chaotic systems, in random systems, can be harnessed to prove surprising results in various parts of mathematics. Today we will discuss surprising results in number theory, okay? So what kind of number theory do I have in mind? I'm going to, in my talk, this talk is going to consist of two examples, okay? The first example has to do with decimal expansions in base 2 and base 3. Simple topic. The second example has to do with solving quadratic equations, or more precisely, quadratic inequalities in integers. All right. So these are two old number theory problems. And what I'm going to try to communicate to you today is we can use this very different physicsy ergodic theory to study these two problems. Okay, that's the goal of today's talk. All right. So now, ergodic theory happens on what is called a dynamical system. You need a phase space on which you're going to do your dynamics, on which this complicated motion is going to take place. So I want to begin by giving you some examples, an example of this phase space. And we are going to take the phase space to be a circle in the plane. Okay, so imagine in your mind a circle centered at the origin in the plane, the two-dimensional plane of radius 1. Okay? So those of you who have seen this before might recognize that there's a mathematical way of making this circle. And that is by taking the one-dimensional real line, okay, considering the closed interval 0 to 1, and wrapping it around, right? Wrapping the real line around this interval. So this is something which is an important thing, this process. It's called taking a quotient. We're taking a quotient of the real line by the integers. It's it's in the background over here. Okay, if you've seen this before, keep it in mind. If you haven't, it doesn't matter. So our space is going to be the circle. And on the space, I'm going to define a way of moving points around. And it's going to be a very simple rule. The rule is you take a point on the circle, which, as we just described, is essentially just a number between 0 and 1. You take a number between 0 and 1, multiply it by 2. Okay, so if you multiply it by 2, the resulting number might still be in the interval 0, 1, or it might not. So what you do is you go mod 1, right? You take the remainder. So this results in always giving you a number between 0 and 1. So it's a very simple rule. Take a number between 0 and 1, multiply by 2, and take the remainder. It will always land in 0, 1. So you get a rule, a map which sends a point in 0, 1 to another point in 0, 1. It sends a point in the circle to another point in the circle. Similarly, there's nothing special about 2. I could multiply by 3 as well. Okay. And these are very simple maps. And the question that we want to address is very simple, right? So this thing is, suppose I take a point and keep on applying this multiplication by 2 or multiplication by 3. Can you predict what is going to happen? That's the question. All right. It's a very simple question. And this is a toy example of what is an ergodic system. Okay. So as we will see, nature is very complicated. So there's still essentially quite basic questions about these toy models, which we still cannot understand. But let's first venture into trying to see what happens. Okay. So here is a definition for us. The definition is a subset, a part of the circle. So this notation T is meant for the circle. Okay. The reason I call it T is because we mathematicians, we call the circle torus sometimes. So that's why there's a T. But never mind. This is meant to be the circle, and I'm saying that a subset, a part of the circle, is invariant under this times 2 or times 3 map if under this map this subset is sent to itself. Okay. So what does this mean? It means that there are pieces of the circle to which multiplying by 2 does not do anything. It doesn't change the piece. It might change individual points in the piece. I'm not saying that every single point cannot be moved by the map, but if it is moved by the map, it's moved to some other point within the same piece. So as a whole, the piece doesn't go anywhere else. Such a subset of the torus, the circle, is called an invariant subset. Okay, and this is a basic theme in all of mathematics, that given a mathematical structure, one of our main goals is to classify mathematical objects which are invariant under the structure. All right, so this is somehow think of it as the mathematical version of the building blocks of a theory. So invariant sets are kind of a building block for this theory, and if you have a good understanding of all of them, then it goes a long way in understanding the complicated system. Okay. So my goal would be, as a mathematician, would be, all right, here's a nice complicated map, which is this multiplication by 2. Can I write down a list of all the invariant subsets of this map? Okay. So it turns out actually that there are many invariant subsets for this map, and I'll show you some. Okay. The first example which would have come to your mind already is that the circle itself is invariant because the map is from the circle to itself. So this is kind of a, it is an example, it fits the rule, but it's kind of cheating, right? It's a silly example. Everybody knows that the whole thing is going to be invariant. What's the big deal? Okay, so that's true, but not interesting. Can I give you something interesting? Yes, I can. And a very interesting example is the so-called middle third character set. So this is invariant for multiplication by 3. Okay. So here's a picture of the middle third character set. So I want to ask, have people seen this kind of thing? If not, I'll do a small introduction to it. So should I have a small introduction to the can? Have you guys heard the term before?
Anish, they cannot unmute themselves.
I see.
Yeah, I request the participants to write in the chat section. Oh, so they are writing, no, sir, we haven't.
Okay, all right, fair enough.
Sure.
Okay,
sure.
Thanks. All right, so this is a beautiful set. It's a beautiful construction due to the famous mathematician Cantor. And as you can see, it's explained in this picture, right? So you take the closed interval 0, 1, and what you do is you have a kind of iterative procedure. In the first step, you take out the middle thirds interval. Okay? So you have 0 to 1/3, 1/3 to 2/3, 2/3 to 1. You take out 1/3 to 2/3 and throw it away. So you have 2 pieces left. In the second step, you do the same with the middle third of the remaining 2 pieces, throw them away, and you keep going, right? You keep on doing, you go forever, infinitely. At the end of this, right, you'll be left with some kind of dust on the real line, okay? So you might think, okay, this is interesting. Let me think about it. So I removed 1/3 in the first round. Then I removed 2 parts, and then how many? 1, 2, 3, 4, 5, 6, 7. And I keep on doing this. So how much have I removed, right? So if you take out your paper and pencil and do a small calculation, you can see that the lengths you've removed form a geometric series. And they add up to 1. Okay, astonishing, right? You started with an interval of length 0, 1. The interval from 0 to 1 of length 1. And you have somehow got a process where you're removing intervals at each stage whose total length adds up to 1. So you seem to have removed everything. But in fact, what remains, the dust that remains, is a lot. Okay, it's uncountable. Okay, it's what is called. So there's a theory, a mathematical theory of integration, where we all learn differentiation, integration, and so on. There's a more sophisticated theory called Lebesgue integration, which is somehow the more standard mathematically used theory of integration. And this theory allows you to measure the size of sets such as this. Okay? So this set in Lebesgue's theory has 0 length. It's an uncountable set of 0 length. And that kind of makes sense because we took away all the length. But, like in the other sciences, like in biology, so on, if you have something that you can't see, a microorganism, what do? You put it under a microscope and then you adjust. Okay? There's a mathematical microscope. Okay? And when you put on the mathematical microscope and try to focus properly so that you can see the Cantor set, it gives a value, a dimension value to the Cantor set, the adjustment. And this value, the dimension, this is called the Hausdorff dimension of the Cantor set, is log 2 by log 3. So it is a this is something which, you might have heard the term fractal used in, popular science. This is an example of a fractal. Okay, so it's a set which is kind of hard to visualize. It's just dust, but it's in the correct setting of the microscope, it is quite big. Okay. So this is an example of a set on the circle. When you multiply one of these dust things by 3 and go mod 1, it will send you back to the same dust. So it's a very interesting example of an invariant subset for times 3. Hang on, let me check the chat. So the question is, there's a question here that says, are we scaling our interval? So you mean in the Cantor construction, what we're doing is we're just removing chunks at each level, right? So it's an iterative procedure. At each level, we remove one set, and then we keep going. So what is left is just the intersection of everything that remains. Okay, that's what it is. I hope I've answered the question. If not, please feel free to continue the chat. Okay, so this is an invariant set for times 3. And there are many other interesting examples. So this already tells you that there's something going on over here. So let's try to understand what that something is. Okay. So this is a kind of technical point which I'm not going to talk about. Let's ignore this bullet point and go to the next point, which is what the. So the point is that every real number has a base p expansion for any p. So it has a base 2 expansion, a base 3 expansion, and so on and so on. Okay, what does this mean? It just means that you can write a real number between 0 and 1 in the following form. You can write a 0.x1, x2, and so on as this infinite series where each of the coefficients xi are in. So let's say that I take p equal to 3, base 3 expansion. So all these coefficients xi will be either 0 or 1 or 2. Okay. This is something we're all familiar with. I can expand a number in base 2 or base 3 and so on. Right? And it turns out, in fact, that essentially this expansion is unique, which means that the base 3 expansion of a number essentially determines the number. This is a kind of a little bit, there's a little bit of cheating going on for rational numbers, but it doesn't matter for us. Okay? Let's not worry about it. And rational numbers, numbers which are fractions, 2 over 3, 4 over 5, these are characterized by having expansions which are eventually periodic. So after a point, you see the same pattern again. And after a point, you see the same pattern again. So they're periodic. So this expansion gives you a pattern of zeros, ones, and twos. And the zeros, ones, and the pattern of the zeros, ones, and twos tells you a lot about the number. Okay. All right, very good. So let's consider multiplication by p, for example, 3, right? Multiplication by 3 on the circle. Then, in the last slide, what I told you was that given a number in 0, 1, I can write it out in base 3. Okay. So now you can say, well, all right. So now if you do this multiplication by 3 mod 1 map, what happens to this base 3 expansion? Can you write it down in terms of the base 3 expansion? And the answer is yes, I can. Okay. It turns out that the times 3 map, multiplication by 3 map, just shifts the expansion by 1. Okay. So if I started off with a number whose base 3 expansion is 0.x1, x2, and so on, after applying this times 3 map, what it does is it just eats up the x1 and shifts it. So the new number that you get by applying this map has a base 3 expansion, which starts with 0.x2, x3, and so on. Okay, so this map is very simple to understand in terms of the expansions. Once you expand a number in base 3, applying the map multiplication by 3 mod n just means shifting it. And then if I want to apply it again, I shift it again and it will eat up the x2, and so on and so forth. Okay. All right. Okay. So, what I started off with was an example of a system, it's times 2 times 3. Then I explained that it's very good to know what are the invariant subsets for these systems. They are the building blocks, they're the atoms of the system, so it's important to know what they are. And then I exhibited for each of these, for times 2, for times 3, many invariant subsets. Right? So for times 3, there was a scatter set. There's a similar construction for times 2. Okay. So now the question is, it's a natural question. So the original question that we asked, namely, if I multiply points of the circle by times 3, can you write down these building block invariant sets? And the answer is, I can. I can. There are lots of them, but using this symbolic coding, this expansion in base 3 and base 2, I know how to write these things down. I can do it. All right. A slightly more interesting question is the following. Take a real number between 0 and 1. And you can say, well, okay, you expanded in base 3, but I want to expand in base 5. That's also allowed. I can do it. Now the question is there any connection between expansions in base 3 and base 5? In base 2 and base 3. I start with one number, expand it in base 2, then expand it in base 3. Are these two connected? If I see these two expansions without knowing the number, can I say anything? All right. If you convert this question into the language of multiplication by 2 and 3, the question becomes, are there subsets of the circle which are invariant for both multiplication by 2 and multiplication by 3? We just saw that there are many which are invariant for each of them, for 2 and for 3. The question is, are there any ones which are jointly invariant? Okay, so I'm looking for a piece of the circle which doesn't change when I multiply by 2 and also doesn't change when I multiply by 3. Okay, so this piece would consist of numbers whose decimal expansions, whose expansions in base 2 and base 3 have some common symmetry. Okay. There's something in the chat. So the role of mathematics in advancing technology and what would happen if mathematical gap is created in society. All right, that's a very good question. Maybe I can come to it after I finish, right? It will take me a little too far from what I'm currently talking about. So maybe I'll try to, after I wrap it up, I'll come to this kind of thing. So Professor Saxena, it's 1 hour, right? Is it?
Yes, I mean, around 50 minutes.
50 minutes, okay.
50 minutes, and then 5 to 10 minutes for Q&A. But because you are taking the question answer in between, so in any case, by 7 o'clock, yeah.
Okay, I'll thank you.
Sure.
All right, so the question is, there are two interesting maps on the circle, multiplication by 2 and multiplication by 3. Can we have subsets of the circle which are jointly invariant? And the number theory question, which is the same question, is, do expansions in base 2 and base 3 have anything in common at all? So this turns out to be a very difficult question. All right, so this is when I first saw this kind of question, after seeing the fact that it's relatively easy to write down what happens for each map, I really thought that it would not be too difficult to write down what happens to both the maps together. But actually, it turns out to be very difficult. So let me tell you what is known and what is not. So let's call two integers multiplicatively independent if they are both not powers of a single integer. Okay, so what this means is that if p and q are multiplicatively independent, if when I take log p and divide by log q, this is not a fraction. It's not a rational number. It's not a fraction. Okay, so what are some examples? So 2 and 3 are multiplicatively independent because log 2 by log 3 is not a fraction. 2 and 6 are multiplicatively independent, but 4 and 8 are not. Okay, all right. So here now is a famous theorem of mathematician, very famous mathematician called Hillel-Fürstenberg. So this, you know, in maths, they have this, they don't have a Nobel Prize in maths, right? So I don't know why that is. People have various stories, but let's not peddle stories because as Professor Saxena says, this talk is being recorded, so I should be careful what I say. However, there is a substitute called the Abel Prize, given for lifetime achievement in mathematics. And Professor Fürstenberg was awarded this in 2020. So he, in 1967, published a landmark paper where he proved that if you have two numbers, p and q, which are multiplicatively independent, and if you look at multiplication by p and multiplication by q, for example, 2 and 3, then the only invariant subsets, there are only two kinds of invariant subsets. Either is the whole torus, the whole circle, or it's a finite set of rational numbers. It's a finite, like 5 numbers which are fractions. That's it. Okay. So, for example, it completely rules out all this Cantor set that we construct. Not allowed. Okay. So it's a beautiful result, and it's a very startling result because individually each system has, you know, thousands and thousands of invariant sets. Together, suddenly the options go from thousands to 3. That's it, right? So this is an example of a phenomena in mathematics which is called rigidity. Okay, namely that together these two systems are rigid. Now, there is an analog of this whole thing in ergodic theory, where instead of using sets, you use what are called measures. Okay, so I remember I spoke a little bit about this Lebesgue integration theory. So the key construction underlying this is the notion of a measure. It's some kind of object which tells you how to measure the length of you know, subsets of the line or of the plane. And it's a fundamental problem to, you can make sense of an invariant measure. Okay? And it's a fundamental problem to determine which measures are invariant under things like times 2 and times 3. And to this date, we don't know which measures are independent under times 2 and times 3. So there is a conjecture of Fürstenberg, which is a very famous open conjecture, which says that there is a similar statement should be true for measures. Namely, if you have two measures, if P and Q are multiplicatively independent, and if you have a measure which is an ergodic invariant measure, so the ergodic invariant measures are the building blocks of all the measures, then the measure should either live on the circle completely or be supported on some finite set of points. This is a problem which is still open. Okay, in a particular case of this, it's fair to call it a particular case. A particular case in a slightly different setting was proved by another famous mathematician called Elon Lindenstrauss, along with his co-authors, Heinz Ziegler and Tata. And for this, Lindenstrauss was mainly for this and for some other beautiful work, he was awarded the Fields Medal in 2010 in Hyderabad. Okay, so this brings me to the end of this part of the talk. So this was an introduction to what is an ergodic system, what is a dynamical system, what would one like to do with it, and the upshot, what I want to leave you with is that these are you can start with very simple systems and suddenly encounter grave difficulties. Difficulties which in some cases, like in Fürstenberg's beautiful theorem, have been resolved, while in other cases, they are still open. Okay, so all of you in the audience who are, bright young mathematicians can start trying to prove these famous results. All right, so I'm going to skip a few slides and go to my second problem. I remember I said I was going to present two examples in the talk, and this is the second example. Okay? And this involves quadratic forms. Okay, so do we all know what a quadratic form is? It's just a expression of the form ax squared plus bx plus c, for instance. Okay, so ax squared plus bx plus c is a quadratic form in one variable, which is x. And when we were in school, we were told how to solve such equations. So if I set ax squared plus bx plus c equal to 0, all of us know how to solve for x, right? So this is very nice, good thing. But in number theory and in many real life situations, one not only wants to solve these equations, but to solve them and get integer solutions. Okay, so when I plug in the formula for a quadratic equation, I get some, complicated fraction with a square root. And there's no guarantee that after simplifying and so on, I'll get an integer, I get a natural number. No guarantee at all. So how to find natural numbers or integers, positive, negative, which will solve a quadratic equation? This turns out to be a highly non-trivial issue in general. Right? Let me remind you of one of the most famous such problems, which is Fermat's last year, which says that if you take, the family of equations x to the n plus y to the n equals z to the n, and if you look for solutions with n is at least 3. So if you look for solutions to the equation x to the 5 plus y to the 5 equals z to the 5, then in fact there are no non-trivial solutions. 0, 0, 0 is a solution, but there are no non-trivial solutions. And as we know, this was one of the most outstanding open problems in maths, and it was finally solved by Andrew Wiles in the early 90s. So we are now going to try to tackle a similar kind of problem, and we're going to try to invoke ergodic theory. Okay, so let me present to you a theorem called Meyer's theorem. It's a German mathematician. It says that a rational quadratic form in 5 or more variables always has a non-trivial integer solution. So a rational quadratic form is just a quadratic form whose coefficients are rational numbers, fractions or integers, okay? So I'll skip 1 or 2 bullet points here because there is a little bit of slightly complicated maths going on, which I don't want to mention. So here's an example of a rational quadratic form. There are 5 variables, which I've named x, y, z, u, and w. And there is a quadratic form, which is simply x squared minus 5y squared minus z squared plus 2u squared minus 8v squared. So this theorem, the theorem that this gentleman Meyer proved, tells you that this, if you set this equal to 0, you will find integers x, y, z, u, w, which will solve this equation. Okay. This is kind of, you know, if someone tells you to solve this thing, I would not know how to do it, frankly speaking. There are 5 variables, who knows? I mean, you guess once or twice, after that you give up. Right? What he tells you, what Meyer guarantees is that there will always be a solution. Don't worry. He's not telling you what it is, but he's telling you there is a solution. Okay? That's the theorem. So this is a kind of a class of theorems in mathematics which are existential. Okay, so you can use sophisticated mathematical techniques to say that there definitely will exist a solution, but it might not give you the solution. Now, what you can do instead of looking at forms like this is ask, okay, so what happens if I, instead of having a 5 here, I have something like the square root of 2. That's also a quadratic form. What about that? Is it possible to solve an equation like x squared minus the square root of 2xy plus the square root of 3z squared equal to 0 in integers x, y, and z? Is it possible? And you know, if we took an audience poll, or if I asked you, you would say, look, this doesn't seem right. At least over here, you know, everything was an integer or something. 1 minus 5 minus 1 plus 2 minus 8. Here there's all sorts of nasty, you know, minus square root of 2 plus square root of 3. I'm not sure that you can guarantee a solution in integers, right? That's what we would say, just having a look at it, for no reason, but just, it feels like it shouldn't have a solution. And in fact, there is no guarantee that it will. Okay. What is the next best thing you can expect if you don't have a solution? The next best thing you can expect is that they almost have integer solutions, namely that you can solve, rather than solving the equation, so let me go back one slide. Rather than solving the equation x squared minus square root of 2xy plus square root of 3z squared equal to 0, I can't solve it. I don't know how to solve it. But I can make it as close to 0 as I want using integers. Okay. This quadratic form with 5 variables can be exactly solved to 0 with integers. This quadratic form does not have integer coefficients, and this cannot be solved to 0 using integers, but it can be made as close to 0. So for example, we can play the following game. You can give me a number like 1 over a million. 1 over a million is a number which is quite close to 0. I can make this, I can find integers x, y, and z such that this expression is less than 1 over a million. You can say, okay, maybe 1 over a million was too easy. I will give you 1 over 25,000 million. I can still find integers x, y, and z, which will make this expression less than 1 over 25,000. That is the statement. This is a theorem of another very famous mathematician who, along with Furstenberg, won the Nobel Prize, called Gregory Margulis. Okay, he proved this statement that he proved that this game that we are both playing can always be won by me. Namely, you give me a very small number and try to force me to make this expression smaller than that number with integer entries, and I will do. The fact that I can do it is a theorem proved by Margulis. And the story is very interesting how he proved it, because it actually, so this statement that something like this could be done was conjectured by a British mathematician called Oppenheim quite a long time ago, in around 1930. Okay, and it was unsolved for a long time. And then about 55 years later, I work here in the Tata Institute. Somebody was giving a lecture on this problem. And in the audience, there was a famous Indian mathematician called M.S. Raghunathan. And M.S. Raghunathan found a connection between this problem and the kind of problem that I was talking about on the circle to you previously. Okay, he found a connection of this problem to some kind of higher dimensional version of the circle, multiplication by 2. And once Margulis saw this connection, he was immediately able to solve this problem. Okay, so it's kind of a very surprising thing. I don't have the time to explain what the connection is, but let me say that there is a kind of higher dimensional analog of the torus, which I've drawn a small picture of here. It doesn't make sense, but it's a higher dimensional analog of the circle. And on this, there is an analog of this multiplication by 2 by 3. And you can connect the problem of solving these equations, this kind of inequalities, to some dynamics on this higher dimensional circle. So I'm almost at the end. So let me say, so this is great. What do I do? Right? So one of the things that I have done recently is exactly this kind of thing. So Margulis's theorem, like this Meyer's theorem, tells you that I can make this as small as I want. I can make it smaller than 1 over 25,000 million, as I said, by plugging in integers x, y, and z. But it's also an existential theorem. It tells you that these things exist. Now, when I saw this, I wanted to find them, right? Because usually, if I solve something like this and tell you such a solution exists, you may not be very happy. You might say, well, that is no good to me. I want the solution. I don't care if it exists or not. What is the solution, right? So my work recently has been to try to develop some kind of probabilistic technique which will produce solutions for this kind of system. So it's a it's so to give you an analogy, when I started the lecture, I was discussing the motion of gas molecules, and I said that what the observation that started off ergodic theory was that over long periods of time, these molecules equidistribute. Okay, and that's a great thing, but it doesn't tell you where the molecule is at a given time. If I say, okay, can you tell me 10 minutes after the molecule starts, where is it? Can you tell me approximately where is it? And the original theorems of ergodic theory don't tell you that. This is a similar, it's a very similar situation here. These theories which use ergodic theories tell you that, the solution exists, don't worry, it'll be fine. But now what I and a lot of people are involved in is an attempt to make this theory effective and produce actual solutions which can be used. So that is what I've been recently involved in. All right, I think I'm essentially out of time, so I'll stop here. And thank you very much for your patience. And please, any questions are here. Thank you.
Sure. Thank you very much, Professor Anish, for enlightening all the students, faculty members, and the teachers who are there in the group. I do understand asking questions through typing out in the chat may not be a very good idea. So, so I request the attendees, if they want to ask one or two questions directly, you can please raise your hands. Then I'll allow you to unmute yourself, and then you can put up the questions in that case. Yeah. So we'll just wait for a while. Anyone?
So maybe in the meantime, I can address this question about the role of mathematics in advancing technology.
Sure, please.
So it's a very good question. So I would say that, I think, so I'm kind of a blue skies mathematician. So I'm a pure mathematician. I do mathematics for the sake of mathematics. But of course, mathematics has a role in advancing technology, all of science. Right? So this is why this kind of beautiful lecture series that Professor Saxena has organized is so important, because all of science is important in advancing our society. So we need to kind of, not only is it not desirable for a mathematical gap, but not the gap of in any scientific discipline. You will never know as a society which scientific discipline you are going to need. Right? For example, who would have thought that essentially within a year of kind of once in a lifetime pandemic, you would have a vaccine. Right? So somebody somewhere, some group of people were working on it just like that. Right? They were doing science because it's interesting and because it's hard, and then suddenly it became very useful. So we should keep an open mind, not just maths. Try to keep an open mind towards whatever science you're studying, and try to keep as updated as you can.
Sure, thank you. I completely agree. There is one question by Indulekha Kavila. If you can.
Yes, that's a very good question. The question is the dimension of the higher dimensional torus related to the number of areas in the map? Yes, it is. It is absolutely related. It is exactly, okay, so this higher dimensional torus is, it's kind of, if you know some group theory, it's a non-abelian kind of quotient. So what one does is, if you take a 3-variable quadratic form, one looks at, there's a group, which is a Lie group, which is leaves this form invariant. Okay, so so one looks at the action of this group on a quotient of the special linear group of matrices on determinant 1. So that is the kind of thing. But of course, yes, you're right. It is related, very much related.
Yeah, I think there is one more by
Yes,
Ritesh.
what kind of geometrical figure can be expressed by a quadratic form in 5 variables? So, right. So this is a good question. So let me kind of explain a little bit. So the kind of forms that we were seeing had both, if you notice, they're both positive and negative values. So such forms are called indefinite forms, okay? As opposed to forms which only take positive coefficients like x squared plus y squared plus z squared equal to something, right? Which is like a sphere. So these figures form what are called hyperboloids. Okay, they're two-sheeted hyperboloids. So imagine, like all math, I mean, I'm not, I do geometry, but like most human beings, what I do is I do the three-dimensional version in my head, and then I try to extrapolate on paper, right? So 5 variables is something which is out of my imagination, honestly speaking. But what we do is we build up intuition on 3 variables, and then we have enough mathematical theory which allows us to rigorously treat 5 variables. So in 5 variables, a positive negative coefficient form is going to define what is called a two-sheeted hyperboloid. So it's kind of it goes like this. So it curves inwards. That's kind of important, right? So how would I describe it? If you take a sheet of paper, right? Then it's kind of, it's going to curve inwards. So there are 2 sheets like this. So if I draw a triangle on the sheet of paper and then turn the sheet of paper into a hyperboloid, then the sides of the triangle will go inside. Okay, so it curves negatively.
Sure. I think there is one more question that could be, I can take the last question as, yeah.
Okay, so will this idea extend to say unit spheres in higher dimensions and cubic quartic forms? Okay, that's a very good question. So the first remark I would like to make is that this theorem, the quadratic form theorem that I said, does not apply to the unit sphere because it's the unit sphere is a positive definite quadratic form, whereas the theorem that I said is only valid for indefinite forms. So it has to have a plus and a minus. That's point 1. There are similar questions for positive definite forms. Maybe if you're interested, send me an email and I'll tell you about it. The second question is, can you extend it to cubic and quartic, etc. forms? And the answer is yes, you can. But it gets progressively very difficult. And that's the honest truth. So we know quite a bit about quadratic forms, but even there, we're kind of, there's still room to understand. For cubic and higher degrees, it's more difficult because somehow I briefly mentioned that I was using a symmetry group, and it's important to me that the symmetry group is kind of large. It allows me some way of doing this ergodic theory. When I go to a cubic form, it becomes very small. And so this is kind of a challenge. We have been able to overcome the challenge in some cases, but generally speaking, it's kind of difficult. So this theorem can be described as circle, ellipse, hyperbola for different values of variables. So to describe this theorem geometrically, I would say that there is a two-sheeted hyperboloid, and you can give me, you can ask me to find vectors with integer coordinates as close to this hyperboloid as you want, and I will be able to do so. That is a geometrical description of this.
Sure. I think, yeah, must have satisfied the 2, 3 attendees who have been asking it. And that shows how well you have been able to, to raise that bar and the inquisitiveness that has come up after your lecture itself. Thank you. Thank you
No,
very
thank you
much.
very much. It
Yeah,
was a
thank you very much,
pleasure.
Professor Anish. And thank you very much, all the attendees. And on behalf of the organizing committee, that is the Nasi Delhi chapter and the host institution, the Deen-Dayal Upadhyaya College, I would like to thank both the speakers as well as all the attendees for being there with us. Thank you very much.
Thank you. Okay.
Thank you. Sure.
Bye.